Okay, welcome back. So let's start looking at free fall. So it's just like we did, but it's an object which is moving under the influence of gravity. We're talking about one dimension still, so now we're talking about vertical motion. And we're talking about near the surface of the Earth. So we have constant acceleration. It's always 10 meters per second squared downwards, but I'm never going to tell you that. I'm going to tell you it's free fall. When it gets to 2 dimensions, it will be a projectile. Now, these things clearly need a firing device. And these equations only apply when there is constant acceleration. And acceleration is linked to forces. So they only apply when there's a constant force. And the constant force is the weight of the object, you know. If there's additional forces, this equation does not apply. So while it's touching my hand, it's not in free fall. This equation does not apply. And it starts applying once it leaves my hand. And it applies all the way, even when it's at the very top. And it applies all the way down until the instant before it touches my hand again, or the floor, or whatever. So the final velocity for the free fall journey of this pen is not 0. I know it's 0 when I put it in my pocket. I know that eventually it's going to stop because I'm going to stop it. But the free fall journey begins the instant it leaves my hand, and it ends the instant before it touches my hand. It's when only gravity is touching. So one common mistake is people say, well, it's going to be 0 because you stop it. It hits the floor. It hits the ocean. It's stopped. That's not the end of the free fall journey. The free fall journey ends just before it touches the water, or just before it touches the field, or just before it touches my hand. So you've got to watch out for that. And then the other thing you've got to watch out for is people sometimes think that free fall is when you're falling. And free fall technically is any time when only the force of gravity is acting on the object. So any time from the time it leaves the firing device, which in this case is my hand, on its way up, it's in free fall. On its way down, it's in free fall. At the very top, when it's momentarily stationary, it's in free fall. And I guess the justification for that, I guess I can justify that, is that, and I'm going to draw a kind of bit of a graph here. So if this is vertical position and that is time, and I had no gravity, as I threw that pen upwards, it would do that. I'm sorry, this is y, and this is t. So as I go to different times, I get steadily different positions. Agreed? And what really happens is, because of the effects of gravity, I get that. So I get this object goes up, stops, and comes down. Can you see how the actual position, even on the way up, is lower than it would be if there was no gravity? So you've fallen a bit from where you should have been. And that's the logic behind it's in free fall even on the way up. When you stood still, well, you're there, but you should have been there by now. And certainly here, you're there and you should have been up there. So free fall it makes sense. It's not as logical as we might think it is because it's not falling. But it fell away from where it should have been, even on the way up. You know? So it's just a technicality. Don't get caught by thinking that free fall is only the downwards journey. It's not. So we say freely falling objects, we disregard air resistance because it complicates things. All objects fall towards Earth with the same acceleration. So big objects, it's 10 meters per second squared. Little objects, it's 10 meters per second squared. Tiny objects, it's 10 meters per second squared if there's no air resistance. Freely falling body is an object moving under the influence of gravity only, regardless of its initial motion. You could have thrown it down, you could have thrown it up, you could just let it go. All cases, as soon as it leaves your hand, it's in free fall. objects thrown upwards or downwards or those released from the rest are all freely falling once they are released. And once they are in free fall, all objects have the same acceleration, which is, as far as we're concerned, 10 meters per second squared downwards. So the acceleration is the same, even if the actual velocity at that instant is different. It's constant acceleration. Can you see, actually, by the way, how the colored pens kind of help? You know, do all your velocities in blue, all your accelerations in A. You'll never get those two confused. Typical question scenario. I can have you jumping off a diving board, jumping off a building, jumping off a cliff. You tend to jump off stuff. I could have you jumping onto a table, you know, standing on the floor and jumping onto the table. That's a scenario. Hidden information in these questions. The diver's acceleration is minus 10 meters per second squared throughout her journey. I'm never going to tell you minus 10. I'm just going to say, hey, diver jumps off a diving board. You have to know that that's free fall, and therefore it's 10 meters per second squared downwards. I'm not even going to probably tell you to ignore air resistance because it's, you know, we're in this section of class. You know to ignore air resistance unless I tell you not to. Our default is you ignore air resistance. When the diver steps off the board, that's like engineering speak for you just step out and there's no upwards velocity and there's no downwards velocity. You start off with VI equals 0 for stepping off the board. If I say the diver jumps up off the board, there's going to be a positive initial velocity. If I say the diver, I don't know how to say it really, pulls themselves down off the board, they put their hand on the board and they pull themselves down, then there'll be a negative initial velocity. A diver has the same speed at any height. That's the wonderful thing about no air resistance. What gravity takes away from me on the way up, so I'm there, and gravity slows me down on the way up, it gives me everything back on the way down. So when I'm at the same level, I have the same speed. I've got an opposite direction, of course. But in the absence of air resistance, your speed at any level is the same. Final velocity of the diver is a vertical position just before she reaches whatever she's going to hit. Not 0 because she hit something. It's that instant before. And the displacement produced by the journey is negative if the final position is lower than the initial position. The displacement for this journey is minus 7 meters. If that from there is 7 meters, it's minus 7 meters for delta x because she ends here and she starts there. And that is a negative. Final address minus initial address is negative. Okay? So watch out for that. Again, I'm not going to tell you the displacement. I'm going to say the board is 5 meters above the water. You've got to figure out what sign is it, what does it mean. So there's interpretation. What makes this kind of like more interesting, you know, and initially more challenging is that I don't have to ask you about this entire journey. I could ask you about starting here, and I could ask you to end the journey there. I could say how long it is before you reach the maximum height. I could say how high above the board is the maximum height. I could say what is the final velocity when she's at the maximum height. That's a conceptual question. It's 0. I could say what's the acceleration at the maximum height. That's conceptual. It's minus 10. I could start the journey here and say, how long is it before she passes the board on the way down? I could say, how far does she fall from her final height to the board? I could say, how long does it take her to reach the water from her highest point? I could say, how far does she fall in reaching the water from her highest point? I could start you off here and say, how long does it take it to from passing the board to reaching the water on the way down? I could say, how far is it? That's just a conceptual question. It's 7 meters. The displacement's -7 again. I could ask you about her velocity there on the way up. I could ask you about the velocity there on the way down. So there's so many ways I can change this issue. I could reverse things and have a student standing on a table, standing on the floor and jumping on the table. I could be kind of cute and have you, well, no, I can't be cute on that. So can you see how, from my perspective, there's a whole bunch of different visualizations, and they are all the same. They're all the same skill. If you try and remember all the different scenarios, you're going to have like 50 problems to remember. Because I can change what I ask for, I can change the starting point, I can change the ending point. That's, 4 variables and a whole bunch of different start and stop positions. You can't possibly learn all those questions. So don't try. Learn the approach, because it's the same every time. You got to visualize, but once you've visualized, you can extract your information, do your math. It's the same. So I know we tend to cling to what made us successful, and what made us successful is probably memorization in many cases, yeah? And I'm asking you to let go of memorizing that. Remember the equations, but stop trying to remember the problem and start trying to remember the process. And I think it'll go nicely for you. So, diver steps off a high board. The high board is 5 meters above the water. Steps off. So let's draw it like that. This is 5 meters. How long does it take her to reach the water? So I know that my initial velocity equals, what is my initial velocity? Steps off, 0 meters per second. Let's have a look. I know my acceleration, of course, is always -10 meters per second squared, because that's free fall. What is her displacement? -5. Notice if you put 5 down, you'll get the wrong answer, because math is going to be different. -5 meters, because that is the start and that's the end, and that's going in a negative direction, so it's -5. And then I want to find out how long, delta t. So I could say VF, delta x equals VI delta t plus 1/2 a delta t squared. So -5 is equal to 0 times delta t. That's kind of nice. Plus 1/2 times -10 times delta t squared. So -5 is equal to -5 delta t squared. So delta t squared equals -5 over -5, which equals +1. So delta t is equal to the square root of +1, which equals plus or minus 1 second. So delta t, clearly it's after I started, so that's going to be +1 second. So, same old. Draw a diagram, extract your information, make a list, put your equation down, shove numbers in. Can you see how I went from a quadratic form to a very simple find the square root form because that VI equals 0? If she jumped up off the board, that would have been a positive VI, and I'd have been solving a quadratic equation. So the sometimes simple equation, sometimes simple math, sometimes a little bit more complicated math. Can you have a go at this one for me, please? A softball player throws a ball vertically up into the air. The ball takes 5 seconds to reach its maximum height. With what velocity was the ball thrown? So I'm going to put that there. So my advice, if you're taking my advice, is draw yourself a diagram. Doesn't have to be great, but draw yourself a diagram. Show the journey, show what information you know, and then make yourself a list. And then do the math. Get the equation and then do the math. I'm going to just click. I want to just check on something. Oh, very good. Okay. Yeah. Not bad. I'm going to pause my clock so I'm not just burning through. So while you're doing that, I'm going to just, softball player throws a ball vertically upwards in the air. My clock, now it's saying 5. It's saying 0. Here's my start and here's my end. I want to know my velocity with which it was thrown, which is a VI. So, okay, so we did our diagram, and the next thing we're going to do is extract our information, and basically I'm looking on here and I'm going, well, let's have a look. I want my VI, and I know my A is going to be minus 10 meters per second squared, and let's have a look. I know my delta T is 5 seconds, because it says it takes 5 seconds, and, oh, I need one more thing. Man, what do I need? Oh, I know something. I know that at the top, the VF, I know that value. It equals 0 meters per second. It's not mentioned. There's not a number on the thing. It's purely by visualization. So I know that VF equals 0 meters per second. So now I'm on my way. Now I go, well, okay, well, in that case then VF is equal to VI plus A delta T. And VF is 0, is equal to VI plus minus 10 times 5. So 0 is equal to VI plus minus 50. So VI is equal to 50 plus 50 meters per second. And there it is. And the first time you go through it, it takes you an age because you're trying to check things out. And the more you go to the gym, the faster this will get. You know, the more you do homework exercises, the more you just, even though intellectually you know you can do it, if you keep practicing it, it gets faster and faster and faster and faster. It becomes more in your background, and the harder ones then become more accessible. So don't only do the hard problems and struggle through them. It's not this intellectual, oh, I get it. It's like, you're like athletes. You're kind of learning to do this stuff so you can do the easy stuff more easily, and then you can focus your attention on the harder stuff, you know. Diver jumps off a high board with a velocity of plus 15 meters per second. She reaches the water after 4 seconds. What is her velocity as she reaches the water? Can you do that one for me, please? And again, if you're struggling with a diagram, that's the skill you need to practice. And as I look at this, I'm continuing. Just keep on going. I'm just doing this for the people who are stuck on the diagram. So a diver jumps off the high board with a velocity of 15 meters. So we draw ourselves a high board, and jumps up. So I know my VI is equal to plus 15 meters per second. She reaches the water after 4 seconds. So there's my start, and here's my end. And I know my delta T equals 4 seconds. What is her velocity? This is the VF is what I want as she reaches the water. So there's my visualization. Okay. code in. So here we go. So I did my diagram, my visualization. Now my job is to extract the information that I want. I know VI is equal to plus 15 meters per second. And I know A is equal to minus 10 meters per second squared. I know that VF is what I want. And there's one more thing that I need. And what is that thing? Do I know my displacement? 15 meters per second. Oh, 4 seconds, my delta T, sorry. 4 seconds. So I put these guys together. VF equals VI plus AT. It's not always this equation. It's just, I don't know, maybe it's the way I ask the questions, but it's coming up a lot today. So VF equals VI plus AT. So VF is what I want, is equal to plus 15 added to minus 10 times 4. So VF is equal to plus 15 added to minus 40. So VF is going to equal minus 25 meters per second. And that makes sense from an intuitive point of view, because I'm assuming I'm going downwards. It's like it's a reasonable answer. I don't actually know how long it takes me to get to the top, so I could still be traveling upwards, I guess, if the time wasn't long enough. But you know, it seems reasonable. So there we have it. I'm going to stop there. Next time